So welcome everyone to today's AIRAH webinar. For those of you who don't already know me, my name is Marie Karakala and I am AIRAH's Engagement and Program Coordinator. So today's Streamline is brought to you by AIRAH and Ecolibrium, and this webinar will explore AIRAH's newest design application manual, which is the recently released DA07 criteria for moisture control design analysis in buildings. So just before we get underway, if anyone has any questions throughout the presentation, please use the Q&A function, which is located just at the bottom of your screen. And we will allow for some time after the formal presentation to go through any questions you may have. So now I would like to introduce to you our presenter today, Jessie Clark, who will take us through today's session. So Jessie, over to you.
Yeah, my name's Jessie Clark, member of AIRAH, and we've worked for a few years trying to get this DA07 out onto the streets, and it looks like we've finally succeeded. And yeah, it's titled Criteria for Moisture Control Design Analysis in Buildings. So the first thing I want to do is ask you a question. So everyone out in the audience, using the chat box, I want to find out if anyone's out there has an answer or has an opinion on this, which is who thinks Australian buildings should not be more airtight? And if so, why? You can chuck your comments into the chat. And Marie, can you hit the timer there? We've got 60 seconds and I'm going to be quiet now. Well, it looks like we got quite a bit of comments coming through there. Interest in all sorts of things flowing through. But I guess there's going to be a lot of discussion on this at the end of this presentation. But hopefully some of the questions will be answered, like moisture control, for example. I saw the word breathe in there somewhere, but maybe that's a little bit of a misunderstanding, and we'll get to the bottom of that. But the ventilation requirements that someone mentioned is definitely a point of discussion, and AIRAH DA07 tackles a lot of issues with airtight buildings, but so they become more healthy, more durable, and more energy efficient. So the emerging issue, or one of the big emerging issues, is moisture, or what in the building code is called condensation. So the handbook for energy, the condensation in buildings handbook was first released by the ABCB in 2014. And next, you're going to be clicking a lot, Marie. In 2014, the Tasmania Building Designers Guide was also released, which was all about condensation in buildings. In 2016, there was a scoping study for residential buildings, and that was where they found that 40% of all Class 1 and Class 2 buildings had moisture problems, or that the industry reported 40% of all Class 1 houses and multi-residential had moisture problems. In 2018, there was a report on the inquiry into biotoxin-related illness in Australia from the Parliament of Commonwealth of Australia. And in that, Dr. Tim Law was stated as saying the creation of highly energy efficient and fireproof homes over recent years may have had the unintended consequence of increasing the incidence of condensation and consequently increasing the risk of dampness and mold buildup. And he's 100% correct. As we make our buildings more energy efficient, more airtight, then there is a possibility of trapping moisture. But if we do it correctly, those buildings will be more waterproof, more airtight, more energy efficient, more healthy, and more durable. So next, Murray, please. In 2019, the building code was updated and there was a new performance requirement, P 2.4.7, or reflected in both the commercial and residential codes. Next, Murray. And what that states is that the risks associated with water vapor and condensation must be managed to minimize their impact on the health of occupants. So that's an interesting statement, because condensation, yes, okay, liquid water in your construction systems, and minimize their impact on the health of occupants. What does that mean? Well, how do you actually quantify that? It's a difficult thing to quantify, but we can. And next, please. So also in 2019, Condensation in Buildings Guide was updated for Tasmania, the Building Designers Guide version 2. Next. So what do the performance requirements actually, what do the deemed to satisfy provisions that relate to those performance requirements in condensation actually say? They say where a pliable building membrane, so essentially a sarking type material, is installed in an external wall. So we're only talking about walls here. And it needs to be installed in accordance with the appropriate AS 4200 standard. But the key thing is it must be vapor permeable in climate zone 6, 7 and 8. Keep clicking, Murray. And again, and it must be located on the exterior side of the primary insulation layer. So this is talking about generic constructions where you've got fibrous insulation in a stud wall sort of style construction, and then a membrane on the outside for weatherproofing. So in that scenario, then it should be vapor permeable, and that hopefully will solve the condensation problem. So next slide, please. So what about climate zone 1, 2, 3, 4 and 5? What happens there? It's not mentioned in the code. And what if the weatherproofing membrane is not on the outside of the insulation? What if we start doing more innovative construction systems and methods? Then what happens? Next. So the building codes board themselves has stated in some of their literature, or actually in one of their online videos, that the new measures aren't a magic bullet. They're not going to necessarily kill condensation in your buildings. You can follow the NCC, yet they're not going to prevent condensation in all cases. And if you are dealing with an area which is prone to condensation, then there's nothing stopping you, and it's probably a good idea that you go beyond the minimum standards. So basically the building codes board is saying don't use the building code. Do better than the building code, because it's probably not going to solve your problem. Next, please. So enter DA07, and this is what it's going to do for us. It's going to help us design performance solutions, design systems that actually work, that take into account a range of various factors, which is the type of insulation and the different materials you use, as well as the mechanical ventilation, heating and cooling systems. So next, please. So one of the key things that we all know as members of AIRAH is that when you're in different climates, you need different heating and different cooling strategies with potentially different humidification or dehumidification systems. And in hot humid, there's far different requirements, different problems when you've got all the external moisture compared to the cool temperate or alpine regions, where you potentially got a lot of moisture inside the building and very cold conditions outside the building. So the design of the building fabric that works with the HVAC systems is critically important in all those climates. Next, please. The other thing that often gets missed is rain. So we're talking about exterior moisture. How much rain is there in all these places around Australia, and what effect does that have on our building systems in terms of absorption into the cladding materials, and how does that work in combination with the insulation systems and what we're doing on the inside of the building for air conditioning and heating? And what you find with the rain map of Australia is that most people live, and where all the construction happens is where it rains the most. Next, please. So overlaying those two things, you end up with two sources of moisture. Moisture outside the building that might get into the structure, and moisture from inside the building generated by occupants and behaviours, and that is in the form of humidity in the air. So both those sources of moisture, also external humidity in the tropics as well, but those two, two sources of moisture, exterior and interior, need to be managed within the construction envelope, and we can now do that. Next, please. So what we have emerging is what I call the canary in the coal mine. So thank you, Tasmania, for highlighting the issues for us. And the canary in the coal mine, or maybe the canary just outside the coal mine, because mainland Australia is really where all the coal mining is happening. But it is essentially bad news in terms of moisture design and trapping moisture in the building fabric. And Tasmania is doing a good job in trying to turn that around and come up with better construction systems that actually work in those climates. As we increase energy efficiency across Australia, there may be worse problems emerging in climates up to the higher latitudes. Thank you. So the new verification of condensation management in the building code is the other way to comply. Rather than just using vapor permeable membranes on the outside of the insulation systems, you can comply with the condensation by using software or modeling systems that assess the effects of indoor and outdoor temperature and humidity. So what the mechanical engineers care about in terms of comfort conditions inside the building, heating and cooling set points. So what those set points are on your HVAC, rain absorption, wind pressure, solar radiation, material hygrothermal properties, and then if you assess that, is essentially the indoor conditions, the weather and what's happening on the outside of the building, and the materials you use in the structure that are correctly layered to get a good outcome and not trap moisture within the structure. And what we've got to look at that is against the performance criteria or the outcome, which is moisture will not accumulate interior to the water control layer within the building envelope. And that water control layer can be defined as a pliable building membrane, so a sucking type material. New products come onto the market like RABs, fiber cement RABs, rigid sucking materials, which may be exterior grade gypsum boards, metal back pans, which are generally bad news for trapping moisture in the construction system, or it could be the cladding itself in a face sealed style system. But either way, you should not trap moisture within that construction system. And it's interesting they use the word accumulate. So it can get wet, but if it dries out, it's okay. And then the question is it going to create unhealthy conditions? Next, please. So AIRAH DA07. It is, for those of you that have worked internationally or may have experienced working in the US, you may have picked up that the title of this document is exactly the same as ASHRAE 160. And it is because it is essentially the same document with some minor tweaks. And it was reviewed and deemed suitable for the use in Australia and will help us design more airtight, more energy efficient, durable and healthy buildings. And what's contained in the document, I'll just go through a bit in more detail so you know what it's all about. Next. So what it is essentially bringing together different disciplines in order to deliver more energy efficient, more healthy, more durable buildings. We need the ESD, mechanical facade and architecture all working together. The ESD engineers go out and specify an R value. It's not just an R value, it's not good enough. An R value is not good enough. You need to know what the other properties of that insulation is. You need to know whether it's vapor permeable. You need to know if it's a rock wool, a glass wool, a cellulose, any fibrous insulation versus more vapor resistive materials like foam-based materials, XPS, EPS, PIR. They all have different properties, and how you insulate that building has a huge impact on whether you may or may not trap moisture. The mechanical engineers are responsible for the interior conditions inside the building. So how much moisture load is there in the building? What's the temperature? What's the vapor pressure in that building that might force water vapor into the structure or suck water vapor out of the structure? The facade engineers are the poor people that have to try and bring all this together and actually make it work. And in some cases, the architects, well, obviously they have to make it look pretty, but what about roof systems? Who's looking at that? The facade engineers looking at vertical components. So we need to also look at the roof systems and not trapping moisture in the roof systems, and then all the details between the roof systems and the walls. So the junctions like at parapet cappings and things like that. So bringing all this together, you essentially got building enclosure design. And building enclosure design brings all those disciplines together to deliver what I'm talking about, healthy, energy efficient, durable buildings. And DA07 is exactly what the DA07 does. Next. So DA07 addresses durability and health, and it guides the construction type, so selection of insulation based on not just R value, but the vapor permeability of that insulation, the type of insulation, the moisture absorption capacity of the insulation, weather resistive barriers. So that might be a new term, but by that I mean sarking or boards that are designed in the construction systems to drain water out of the construction system. So those weather resistive barriers can come in all sorts of different forms, and all other materials that go around your insulation. and around your weather-resistant barriers, so the cladding materials and internal linings. It will address built-in moisture. Most constructions in Australia get wet during construction, they get rained on, so all the materials in the structure will have moisture in them to start with at occupation stage. That needs to dry out. Resilience to minor water leaks, which has been experienced in other parts of the world where you get some water into the system during the operation of the building, and then the water can't get out and your structure ends up dying. And this is basically what caused the New Zealand leaky building crisis, $47 billion of damage because water got into the structure and couldn't get out. The long-term moisture effects can be analysed with criteria in DA07, so we're looking at mould and corrosion as the two key performance outcomes there. But in terms of health in the building code, it's more about mould. So the guide applies to existing buildings and new buildings. Either, it doesn't matter. Retrofits of existing buildings and putting insulation into existing buildings is necessary to understand how that affects the moisture balance. Next, please. Building class, all building classes, so residential class 1, high-rise residential, offices, student accommodation, hotels, retail, commercial. It works for all buildings provided that building is heated or cooled on the inside of the building, that there's weather on the outside of the building, and you can analyse any of the roof systems or wall systems that provide the thermal envelope between the interior and exterior boundaries. So it can look at envelope systems and new ways of delivering envelope systems. In facades, it can be used for heavy masonry systems, it can be used for lightweight systems. Systems that have large amounts of masonry on the outside of the structure may store moisture in that masonry. What happens and how that moisture redistributes depends on the climate and how you're heating and cooling that building. Next, please. Skip something there. Anyway, so it can also look at drained and ventilated cavity systems. So depending on the software you use, which I'll get into in conjunction with DA07, then you can look at essentially what happens in ventilated cavity systems and what the requirements are there when you've got well-sealed, weather-resistant barriers behind those systems. Next. Residential roofing systems. The criteria in DA07 can be used in any type of residential roofing structures. How you calculate the temperature and humidity within that structure is dependent on the software that you'll be using with DA07. Flat concrete roofs, for example, on high-rise apartment blocks. Do we use insulation, highly permeable, vapor permeable insulation like mineral fiber on the inside of the structure, or do we go for outsulation on the external side of the concrete roof and change the way we insulate the buildings to make sure that we don't increase the moisture content in that concrete or create condensation problems? Next. Or do we do both? And then we can look at that system and say, well, is there going to be any problem? Is that concrete going to get cold? Is it going to increase moisture content in that concrete? That can all be looked at using DA07 criteria and hygrothermal simulation software. Next. So DA07 does explicitly exclude rain penetration. So to some extent, it assumes that the building structure is watertight, but you can look at minor water leaks if necessary. So if we take some guidance from New Zealand off the back of their damages they had, $47 billion of damage in New Zealand from the leaky building crisis, what they did, some clever committee in New Zealand actually worked out that it was a good idea to break this problem down into external moisture problem, rain and weatherproofing, and internal moisture problem, which is the indoor latent heat loads, moisture, vapor pressure on the inside of the building and outside of the building in terms of weather, to come up with healthy building systems that are dry and durable. So the fundamental principles there, what we have in Australia is, next. We're still going, Marie, can you flick that on? Yeah. What we have in Australia is a very similar approach, but not so obvious. We have damp and weatherproofing in one part of the building code. And in that section, it's all about designing systems that are that will stop the rain ingress into, well, particularly facade systems. So it's there in one part. Then in the other part of the building code, the health and amenity, that's where we talk about the condensation and the verification of moisture management. So that's about the drying capacity and not trapping water vapor in the structure. So first of all, we have to make the buildings waterproof, and then we have to analyze the structure, whether we trap moisture. Next. So the weatherproofing is done if you're using a verification method in the weatherproofing of the building code is to do a full-scale weather test. That means you don't get water, or you're designing systems and details that are proven to be relatively robust in stopping moisture getting into the construction system. In order to do that, a weather-resistive barrier is almost always necessary to make that work. And that is a layer like a sarking material or a rigid board system that is well sealed, that is a water barrier and provides a barrier to wind forces. If you get wind entrained through the system, you entrain the water into the system. So weather resistive barrier is used as a term in this standard, and you need to know what that actually means, because that's critical to making the whole system work in moisture management. Once you got the system waterproof, then it comes to the point of health and amenity, where really the only way to judge whether a system is going to be durable in the long term and not trap moisture is to do a computational analysis, because we can't build the system and wait 10 years to see if it rots or goes moldy. So next. So to do that, the computational analysis that DA07 is dealing with is hygrothermal analysis, which generally is a dynamic simulation required that will have temperature and humidity inputs and outputs to the model for every hour of the year, but normally run consecutively for 10 years to work out whether you're going to get moisture accumulation in that system. Next. So what we're looking at, external moisture, rain loads, the risk of rain in certain parts of Australia, the big red parts are where on the left is where it rains the most. Overlaid with the climate and how the system will dry out, you end up with essentially various different methods or different systems that are required to build across different parts of Australia. And this will also be dependent on the building class and how it's heated and cooled on the inside of the building. Next. So this brings us to the supporting software. So DA07 is essentially a guide on how to do, or the criteria required to analyze or to assess a hygrothermal simulation. There's various tools out there in the market or worldwide that can be used for hygrothermal simulation. So WFI you may have heard of, Delphin, Hyg, IRC, 1D, these are all different software packages. There's more, but what they are able to do is assess against that criteria in the building code, which is exterior weather conditions, the internal temperature and humidity conditions, and all the construction materials that are used in that build-up, and in particular the insulation systems and how that relates to all the other material layers in the system. Next. Oh, sorry. Yeah, so when you start getting higher humidity, so that green line is a humidity profile through a construction system. If you induce higher humidity in a construction system, then you start to get into the risk zone where you might start to get corrosion or mold growth, depending on the materials around it. So if there's obviously metals around it, you might induce corrosion. If there's materials that have cellulose-based materials, then you might induce mold growth. Next. So the most internationally validated software tool is WFI. WFI has been used all through, well, the US and Europe for scientific research and validation of construction systems. There's hundreds of research papers from AIRAH that use WFI either in the research paper or to prove certain aspects of design. Next. So what the DA07 does is set the criteria saying, what are the initial conditions, what are the assumptions in that model that I should start with? And one of the key assumptions it has is that you should always start with wet construction materials. And this is because basically every building site either gets rained on or has potential to get rained on. So you wanted to start that simulation with wet materials to make sure that they can dry out and you're not trapping the moisture in, say, the timber stud work. So in that, it says the equilibrium moisture content, which is the moisture content of a material at a certain humidity level. It says if it's a soggy building site, then it should be equilibrium moisture content at 80% humidity and double that. If you have special precautions to stop the site getting wet, this could be something like prefabrication, then the building is built when there is no rain, it's built during sunny weather, enclosed into a weatherproof system, and the materials stay dry. And that's what we want. So you assume that the materials in that case are starting with a much lower moisture content. Next. Other scenarios like CLT, when you've got high-rise CLT level by level, if it starts getting a bit ominous in the weather and gets rained on, then you potentially get moisture into that CLT. So you need to make sure that it can dry out. Other methods might include protecting that CLT so that it never gets wet. Or to limit the risk of it getting wet during construction. So you start with a simulation with a dry structure, but that has to be planned into the construction process. Next. So what DA07 is looking at is essentially the ability of the structure to dry out based on the initial conditions if the structure gets wet to start with. If then you've used materials that might trap that moisture, and then also during the operation phase of the building. And what's critical to the analysis is the design conditions on the inside of the building. So for commercial buildings, generally there's going to be a design temperature and a design relative humidity. So it's relatively easy to work out what that is. In residential buildings, it starts getting a little bit more complex because people may operate their buildings in all different ways. So there's some general rules and algorithms built into the AIRAH DA07, which I'll go into in more detail in a bit. But generally, the heating and cooling set points in DA07 is set at 21.1 and 23.9. But it is possible that you could change those temperature set points and assume something closer to NatHERS if you wanted to, because NatHERS assumes much higher cooling set points in the tropical climates than what DA07 is outlining. So next. So in terms of the indoor conditions in the building, there's 3 different methods. Thank you. There's a simplified method, there's an intermediate method, and a full parametric method for predicting or estimating the internal temperature and humidity conditions. So the simplified method is just saying basically what's the average outdoor temperature, and then assuming an indoor design relative humidity and a standard temperature from that profile. The intermediate method starts getting a little bit more complex because it's assuming that there's a certain amount of infiltration or controlled ventilation in the building that's taking direct outdoor air and mixing it with the indoor air at a certain ratio, and then predicting a internal humidity load based on the volume of the occupied space and how many people or how much moisture generation you've got in that building. So that's the method I prefer. Oops, and there's a full parametric model too, which kind of gets complex, but I won't go into that. So the intermediate method, which you're seeing here, has options around looking at heating only, because this allows you to then select the type of system that you're using to heat or cool your building. And from that, it will predict a internal temperature and humidity. If I then go to air conditioning, it pulls out a lot of the moisture in the internal air in the summer because you've got moisture coming off the coils of the air conditioning. Then if you go to air conditioning with dehumidification, you can cap the humidity in the indoor environment, assuming that you're always dehumidifying to a certain level. And what this allows you to do is then analyze how does this impact the building envelope. The other thing you can look at is select the air tightness level. So you can have a airtight construction or a standard construction. And if I have an airtight construction, it drives up the indoor humidity. Then if I start putting a controlled ventilation rate through, so what this allows all the mechanical engineers out there to do what you can do then is say, if I have a controlled mechanical ventilation strategy in, say, this apartment, you're much less likely to get mold and moisture build up in the building envelope of this apartment block. And the reason for that is because you reduce the indoor humidity in the building, and then the calculation can be made under 2 different scenarios and compared what the risk of mold growth is. Next. The other thing that guide looks at is air transported water vapor. So if there's moisture in the air, if you have air leaks into your structure, and all those air leaks can actually give the moisture a free ride into your structure. And what that does is go get taken to the colder surfaces and then accumulates in those cold surfaces and then potentially causes damage. And this is a pretty important part of the standard in terms of looking at that air leak or air transport of water vapor in the structure. And the reason this happens is because you've got a stack pressure in a building, for example, shown in the diagram. If the hot or the warm humid air is pushed up to the top of the building, then that warm humid air can diffuse into the structure and create moisture damage in the structure by air transported water vapor mechanism. And what you're seeing on the right there is a wall system in a research lab at Fraunhofer in Germany, where they looked at air transported water vapor coming through a small hole in the warm side of the structure and then being transported to the clear perspex on the cold side of the structure. And what you see is a condensation effect happening all over that vapor barrier perspex. Sorry. So that's what, anyway, that mechanism needs to be looked at in using the specific clause in DA07. That's quite important. Durability of construction systems is very important. This is off the back of large damages around the world in the US, the Canadian condo crisis, where the exterior foam systems were used. Water got in behind the exterior foam systems and ended up rotting out everything behind the exterior insulation. And from that, a criteria was developed, which is 1% of all driving rain that hits that facade should be dumped into that system. And then you see how the water redistributes in the system and whether it's likely to accumulate and cause damage or mold growth. Next. So what that is essentially when you've got a system and you're looking at how these systems operate, you use the external weather conditions, dump 1% driving rain behind a face sealed system, and then see what happens to the criteria around mold growth and corrosion. That also is effective if it was just a face sealed fiber cement sort of system. But what becomes critical in those sort of systems is when you've got render coats on the outside and if that moisture can dry back out. So the coating systems are critically important as well. Or you design out the risk and you design better systems that are better drained and have far less risk of moisture getting into those systems, which is probably a better approach to go by. Anyway, so it's just pointing out the different options that you could look at using this, this design guide. So for mold to grow, so this is all about the health aspect of the building code. For mold to grow, you essentially need a suitable temperature, you need moisture, you need a food source, so something yummy like timber or paper on gypsum board, which is cellulose based and mold loves to eat. But if you stop mold and corrosion from growing, so the criteria around mold and corrosion in AIRAH DA07 are the most restrictive. There are other criteria like timber rot, but if the building never goes moldy or there's no mold in the building, then timber rot will never happen. Next. So what it lets you look at is different ideas, different design philosophies around construction system and say, am I likely to get interstitial mold growth behind an exterior fiber cement board? Am I likely to get surface mold on the gypsum, on the paper facing of the gypsum board? Will I get interstitial mold on the WRB between different layers? And you can analyze all this for the different climate zones. Other things that you might want to look at is moisture content in timber. That's critically important for mold growth. You can look at corrosion of rebar in concrete precast. You can look at surface mold, again, on different materials other than just plasterboard. And what it does look at is enable those systems to dry out and redistribution of moisture in materials that store a lot of moisture, like masonry materials. So how does mold actually work? Well, or how does it, what are the, I guess, where did the criteria come from? Essentially, mold will only grow if you have the right temperature and humidity, like I said. But if you take interior comfort conditions, or what's considered interior comfort conditions, 20 to 26 degrees Celsius and up to 70% RH, you never get into the risk zone where mold will grow. So when you start talking about different materials and where mold will grow on materials, the green line is where you've got yummy materials like paper facing on plasterboard. If the temperature and humidity conditions go above that, it will start to grow mold. If it goes above the red line, it will start to grow on more or less favorable substrates as well. So on the interior surface of the building, if the interior humidity on the building never goes above 70%, you're not likely to grow mold on the interior surfaces unless you have exacerbated thermal bridging in that structure. Next. So below green line, happy days. Next. Above the red line, you got a problem zone. So if we then, next, take a structure and you're going to analyze a structure using the criteria in DA07, you might want to look at all the different aspects: built-in moisture, rain leaks, just normal operation. You can analyze with and without rain leaks or with and without built-in moisture. But either way, you can do the analysis. Next. And if you get a scattergram, so this is a simulation of every hour of this simulation, you get a lot of hours behind that exterior foam. In this particular case, by way of demonstration, it is in the risk zone. And you say, okay, is it a problem? Well, what dynamic simulation allows you to do is say that there's a time factor in there. Mold won't grow just because you go over a limit for 1 hour. It takes time for that mold to germinate and start to proliferate. So that's where we get into the mold index, which is outlined in AIRAH DA07, how to calculate the mold index. And a threshold is set of a mold index of 3. And this is off a bunch of whole or international research. It's decades of research that has come up with this. And the mold index of 3 is essentially described as visual findings of mold on the surface with less than 10% coverage or less than 50% coverage of mold under a microscope. So the guide is actually saying some mold is acceptable. It's up to you as an engineer whether you say, well, actually, I want to target mold index of 0 or 1 or whatever it might be, but 3 is where it set the benchmark. Next. So what does that actually look like? When you do the simulation, you're able to output for any surface based on the algorithms in DA07 to say, well, based on the temperature and humidity and time factor at that surface interface, is that mold index going to increase year on year, which you're seeing the orange line? Bad news. After 2 years, you're starting to get mold on that particular surface. After 4 or 5 years, it's reached a mold index of 4. So it's probably not a favorable system to build. If you change the specifications, change the material, the insulation type, you get the green line. So now we've got vapor permeable insulation on the outside of that structure. You get a far better outcome. And that's what we're talking about, selecting the insulation systems and all the materials around the insulation systems not to trap moisture or create conditions for mold growth. The other aspect is what materials are actually in that system, because mold won't grow as quickly on metal and glass as it will on paper facing on plasterboard or timber products. So you can change the materials that are used to build that building as well to give you a different outcome or a different risk of mold growth. Next. So depending on what materials there, for example, maybe fiber cement, medium resistant, a bit of cellulose fiber, timber fibers in the fiber cement, might have timber studs, might have paper facing on the plasterboard, all have different mold sensitivities, and then you can put that into the algorithms and test for the mold growth. If, for example, that wasn't a timber stud and it was a metal stud, then all of a sudden it's like, well, do I care about mold or do I care more about corrosion? And if I get a cold stud, do I get condensation on that stud, which then or very high humidity, 100% humidity for excessive amounts of time that produce very quick corrosion rates? And do I need to thermally break that to keep that stud warm, make sure it doesn't get cold and doesn't corrode? Next. So the corrosion algorithms are also built in, and the most basic form, and what it says in the standard, is a 30-day running average should not be above 80%. So if you did get a 30-day running average at that stud above 80%, there's a risk that that stud might start to corrode out. If then you add a thermal break to it, again, then the corrosion prediction or the threshold may be much more favorable. So you can basically work out what are the thresholds around a pass or fail using hygrothermal simulation. And that's what we're after, setting the industry standard on essentially mold growth and corrosion. Next. So what does it do? AIRAH, just to recap, AIRAH DA07, it can be used in new and existing structures, can be used in any building class, can be used in any climate zone across Australia. You can look at what happens when the structure's wet to start with or when it's dry to start with. You can base it on any interior design, humidity and and temperatures based on the HVAC system operation. You can include ventilation in there to lower the indoor humidity. You can look at the effect of air pressure, air transport of water vapor into the structure. You can look at operation failures with incidental water leaks into the system, and then analyze against two key criteria, which is mold growth index and corrosion. So I just want to make, that's it for all the technical stuff, what's generally in the guide, but I want to basically make a special thanks to all the people that were involved in bringing this to Australia. It wasn't just one or two people. There was a lot of people involved. It was an international collaboration, and it was people from the US, Germany, many people from AIRAH, and thanks to everyone involved in that. And if you want more information on the DA07, then you can contact this man, Brendan Pejkovic, and email him at technical@airah.org.au. And if you want to contact ProClimate, then you can contact us in Australia or in New Zealand. And also, I would encourage you to, if you want to look at the hygrothermal simulation software, WFI, which is the most internationally validated and recognized tool, you can jump onto info@wfi.com.au or wfi.com.au or WFI in either Australia or New Zealand. And that brings me to the end of the discussion and question time.
We have a question there from Cameron, who's asking, what about condensation DTS for EIFS?
I don't believe there is any at this point. Is he asking? I don't know. There is none at this point, basically. So if you want to build EIF system, then I would suggest a matter of course is to do a hygrothermal simulation with a 1% rain leak behind the polystyrene or foam cladding system. And that's why it was developed, that particular criteria, because of all the damages internationally. And fundamentally behind an EIF system, you need a WRB, a weather resistant barrier behind the polystyrene. If not, you're asking for trouble.
Yeah, cool. Thanks, Jesse. We also have someone else who just wants you to just explain the acronym RA.
Okay. Yes, very common term used in New Zealand. I guess it's more well known in New Zealand, but it's a resistive air barrier. And that is actually, well, I guess it's a trademark, probably shouldn't be used, but anyway, it's a piece of fiber cement, generally that's what it's known as, a fiber cement on the exterior side of the frame system that's used as the weather resistant barrier. It may not be fiber cement. There's other products like exterior grade gypsum board that can also be used in that same application.
Great, thanks, Jesse. Just going through the rest of the questions. Have you got them up on your screen there, or are you happy?
Yep, but I'll let you guide the. I guess I'll let you choose, or do you want me to just answer them?
Sure. Either way, you're happy. I'm happy for you to read them out. Otherwise, I can read them.
Have Brands or MB looked at this document for implementation into New Zealand building code? Not that I know of yet, but I'm happy to have a discussion. And whoever the anonymous attendee is, let's talk. John Duver, who do you think should own the process of analysing vapor barriers? How can you ensure the process is carried out to the end when the designs are in flux? For analysing vapor barriers. Okay, so I think what you mean is who should own the process of analysing the vapor permeability on the weather resistant barriers? I believe that is purely in line. I think it should be an ESD job. Because if they're specifying the insulation, they should be then taking the onus to say, okay, what type of insulation and how does that work with the weather-resistant barriers in combination with the facade engineers. So everyone needs to, I mean, that's the whole thing, the building enclosure consultants. Maybe we need new building enclosure consultants. Actually, we do need new building enclosure consultants that understand to the degree necessary all those different disciplines that we're talking about. CLT, explain. Oh, sorry, cross-laminated timber. So cross-laminated timber is mass timber, and I'm not sure what they mean by explain. That's what it means, cross-laminated timber. Big chunks of timber that you build a whole building out of. Which type of expert would normally run the simulation programs? Architects can, and they do internationally. Engineers can, and they do internationally. Different disciplines of engineers. So the HVAC engineers would definitely input into the process, and where they come into it is in reducing indoor humidity using continuous ventilation. But it would probably be, again, I would say ESD engineers, the sustainability engineers should be pulling this together to say, actually, based on the HVAC strategy and based on the insulation strategy, this is how it should work. And then the facade engineers already take the ownership of weatherproofing and that detailing. Do the RESI assumed indoor conditions may be disadvantaged vulnerable occupants who can't afford to heat their buildings to those assumed temps, especially in cold climates? Yeah, if you can't afford to heat your building, if you don't heat or cool your building at all, and the indoor conditions are exactly the same temperature as outdoor conditions, then you have no vapor pressure, so you've got no migration of water vapor, and it's a different outcome. You can change those internal conditions, so I can open up that temperature band and make it 10 degrees heating set point and 30 degrees cooling set point if I want. But the whole point about this standard is to produce healthy and durable buildings, which mean that those buildings need to be heated and cooled to conditions that aren't going to stress the occupants. How do the requirements of DA07 compare to DA20? Good question. DA20 does talk about air sealing buildings and using vapor barriers to stop external humidity coming into the structure. And if you use DA07 with hygrothermal simulation, you'll be able to prove that DA20 is actually correct. You mentioned render. Does the kind of paint make a difference too? Yes. So the kind of paint makes a difference whether you have latex paints or have oil-based paints, then it can basically act as a slight vapor barrier. So when you've got oil-based paints, yes, they can act as vapor barriers. And this can all be taken into account in the simulation software as well. Basic Section J and other energy efficiency initiatives endorse intermittent use of ventilation systems. Has this been considered in DA07? Intermittent use of ventilation systems are basically not relevant because they're only on for very short periods a day. Hygrothermal issues are long term. So if you're going to do anything, you either got continuous ventilation, 24 hours, 7 days a week, or you just assume the building has none. And the 15 minutes that the bathroom fan's on, well, it will make a very slight difference, if any. Would you be running any seminars on how to use Woofy? Yes, great question. So I would jump on to the woofy.com.au, woofy.co.nz websites and have a look there. But our company ProClimate is running Woofy seminars. So also take a look at our website, proclimate.com.au. And there currently are none scheduled, but there definitely will be some coming online very soon. And we're looking at working in collaboration with AIRAH on potentially doing even more through AIRAH as well. What weather files would you recommend using? Good question, Marcus. So internationally, there's I know when you use the WFI, for example, it's linked or can be used weather data extracted from Meteornorm, which is a Swiss software package. And that means that you're essentially synthesizing the weather files. But to some extent, you have to, because we need the rain data, we need hourly rain data. And as far as I know, there's no hourly rain data weather files available in Australia yet as a standardized sort of set of weather files. Lawrence, what building classes are most at risk? And in that context, I would say class 2 multi-res is a big issue. And the reason for that is because precast concrete panels, which are face sealed and often used in the construction of those buildings, inherent by nature, are possibly more airtight than we actually think, in which we drive up the indoor humidity and then the occupants and the strata have massive battles on whose fault it was that it's raining on the inside of their buildings. So if I was going to do anything, I would say if you're building class 2 buildings, you definitely got to do this sort of analysis. Yeah, class 2. And also hospitals, because they're meant to be healthy, so you don't want mold in them. Are there any data available on how long does a condition need to exist for mold grow? Yes, that's exactly what the algorithms in DA07 are outlining, but there's a lot of research internationally from up in Scandinavia and from Germany on mold growth conditions. And if you join one of my WFI training sessions, I'll tell you all about it. Might there be an extension of the climate side of things to New Zealand? Well, Ruth, brands have already developed all the WFI climate files for New Zealand, so that's fantastic. So they already exist, and that's it. You can use it already. You can use DA07 in New Zealand right now. Yes, they are, Jason. It would be exactly the same specification on as AIRAH 160 on the requirements around the weather files. And yes, there are potentially, yeah, it's a big discussion point on weather files and what data to use. RAB is a rigid, sorry, Jason, you are right, rigid air barrier. Next, what are the key differences between DA07 and AIRAH 160? Sorry, yeah, I missed it. So the key difference is that in some points it's just referencing the air leakage standard in the intermediate method for internal conditions, saying that you should, under a building code compliant building for air tightness requirements, so we're saying 10 permeability on the air leakage, you should assume that it's the standard setting on air tightness and not an airtight building. If you're specifically building an airtight building or something different, then you choose a different setting. The other difference is that AIRAH 62.2 is called up for ventilation in AIRAH 160, and AS 1668.2 is called up for ventilation in DA07 in conjunction with AIRAH 62.2 as well. Would 20 to 30 litres enough to ventilate the bathrooms in climates 5 and 6 for a period of 15 minutes? So I would say no. 15 minutes of ventilation per day is probably not enough. What you always want is continuous ventilation. So that's a massive discussion point. But what the DA07 allows you to do is put that argument forward. And DA07 is always dealing with continuous ventilation strategies. If you want to do something like that and come up with a ventilation rate that 15 minutes per day is equivalent to a continuous ventilation of something else, it's a very difficult thing to do. But there are research papers on it out of the US, which I'm more than happy to share. Is there a requirement for manufacturers to specify the hygroscopic of the building materials? No, not yet. it would be good if there was, but it's up to the engineers to push it back to the manufacturer and say, where's your data? Show me your data, then I'll specify your product. The more requests they get like that, the more likely that they're going to test for the hygrothermal data. How up to date is the construction database in WFOE in terms of Australian market? That's a good question, Stefan. It depends how well you know your products, and a lot of the products in the database are equivalent to or directly imported from overseas, but there are products in the database that can be used straight up. So we're working on that as well in terms of developing product data and what should be used in simulations in Australia and New Zealand. Sabina, how can we simplify the use of DA07 for general residential builders? We can develop some short courses and videos, etc., but it needs to be. Nope, this is a performance solution. So this is up to the engineers to engineer solutions. If you want to come up with pre-calculated solutions for residential builders that couldn't be bothered, then what we need to do is hundreds of thousands of simulations like they did in the US to basically spoon feed the residential builders. How the ventilation roof ceiling space affected the total R value of the roof in tropical weather areas? Good question. So this is a very, very big question. Should you ventilate a residential roof space or any roof space in tropical climates? Depends on what, or I think we're talking resi, maybe not talking resi. If you ventilate a roof space, you're introducing a lot of moisture in tropical climates. What you need to know and what further training needs to be done is around how you use control layers. So where those vapor barriers need to be set and how airtight those vapor barriers need to be to stop the humidity coming into the cool plasterboard surfaces. And until you have an airtight, air-conditioned building in the tropics, you're always going to fail. And the ventilation of the roof space is potentially introducing problems, but it depends a lot on the design strategy. If we use WFOE in residential projects in Sydney as a performance solution, any idea of the process to sign off, and have you tried this? Peter Hartigan, no, haven't tried it yet, but there's a verification method in the building code. If we're going to use performance solutions, then that means you're going to do a design calculation, and this is a process by to do it. And it would be great to try this out with you. What is current pricing structure for WFOE? I would say check the WFOE website. That's the best way. How good is the Australian weather data in WFOE now? The Australian weather data, basically, it's using the Meteornorm process and pulling out the weather data from Meteornorm. It's a synthesized weather file from real data in Australian weather stations. When you say how good is it, depends what you mean by how good. There's a lot of dependence on that. But there is also people looking at it, I know, in standardizing those weather data sets. In your own opinion, does the DA07 lack of any aspects? Are there any building physics topics missing that you'd like to see included? Henrik, I think the biggest issue is, which was raised by one of the other attendees a couple of questions ago, which was ventilated roof space and how they're dealt with. And that comes down to the software and how you actually calculate it more so than the criteria in DA07. So that's a big question. But other than that, you're far better to start using the manual and using the software to come up with design solutions. If it's only just for your in-house knowledge, it's still far better than just going in blindfolded and sticking your head in the sand. What does DA07 recommend to remediate mold? It doesn't. It's about design. So it's about designing buildings to not have mold. If you get mold, then that's a different issue. Remediation and making buildings better after they're already stuffed is knock it down and start again. Are there set standards guidelines for building across the various climates in Australia? Yes. So, well, no, not really. There's not build it this way. that's what this is leading to. This is a performance solution. The idea is to get people to develop their own systems that actually work. So you tune in those construction materials and selecting the materials that work in your climate for your building type. And it will come over time, but it's all about industry learning. If we get storm damage, what is the next step? Something COVID shutdown in schools is triggering. That's a remediation question. So it's the same as the other answer. It's how do you remediate that building? There are guidelines. Actually, I'm not sure if there's guidelines in Australia. I'm pretty sure, well, there should be, but there are definitely experts running around in the remediation of moisture in buildings. And I think the remediation side is a different issue as opposed to the design side, to stop the buildings getting wet and allowing them to dry out based on the design phase of the building. Yep, so more WWOOFy training, check the WWOOFy website. Any progress on plans for WWOOFy? How many questions are there? Because this is a... Marie?
Yeah, Jesse, we've got about 6 or so to go.
Okay.
And then we'll wrap it up there, I think.
Yeah, okay. Can the same methodology modelling be used to quantify potential risk of termite? No termites in this. Can the same methodology modelling be used to quantify... Oh, that's the same one. If if that is the case, that the same ASHRAE 160 technically don't meet the wet year 10 years. Okay, thanks, Jason. So that means we need to basically come up with new weather files. Correct. Next. The 15 minutes is for ventilating the bathroom after every usage. Yes, correct. Is a DA07 the ultimate guide, including really all relevant aspects, or is there anything that you would... Oh, that's the same question I already answered, no? Lawrence, good question. I would say build up a database. If you're doing generic systems across different climates, and that's absolutely right, that's the way I believe it should be used. The consulting firms should have generic systems that they recommend, that they've tested for different building classes. And then if they want to do really funky, obscure stuff, then you retest it. But other than that, yeah, build up the database, test it in different climate zones, stress test it under different internal conditions, and make sure that it's a durable system under a wide range of inputs. Yes, so brick veneer wall vents there should always be ventilated cavities, I believe, behind external cladding systems. But when you say wall vents, when you're talking about the wall vents that are designed to allow smoke out of the building because you've got old fireplaces in old heritage houses, that's different. What we're talking about is ventilation from the bottom of the wall to the top of the wall on the outside skin. So yes, ventilated cladding systems are always preferable. Yep, so IAQA is a good source for the building hygienist, definitely. Is there a new condensation verification method supposed to be 1D or 2D? It depends on what you're looking at. I think where we're at in Australia is just getting the material layers correct, and that means it's a 1D analysis of layering those insulation systems and the materials. But when you start getting to 2D, that means you're looking at thermal bridges and junctions, say at slab edges and all that sort of stuff, which is still important. But before we even get to 2D, we need to work out what are those material layers need to be in different climates for different building types to make them work. Just ventilation and sucking fresh air through gaps or cross ventilation. We're talking about continuous mechanical ventilation, so a continuous supply and extract, ideally, which gives you a known ventilation rate through the building at all times. And that's ideally what we want to have to lower the indoor humidity conditions in our buildings. Thank you.
Just Brendan here, Jesse.
Yep.
Before I hand over to Marie for winding up today's session, just like to thank you and everyone for attending. But I'd also just like to remind everyone that Jesse is part of the Building Physics Special Technical Group, who have organised, it's close to a full day Building Physics Forum coming up on September 17. And due to the COVID pandemic, we've decided to make that a virtual event with the focus on moisture control. It did mean we had to cut a 2-day program into a sort of a 3/4 day, but we are focusing it to keep it on the theme of DA07. So for any further information on the upcoming Building Physics Forum and the work that the STG has done, please visit the AIRAH website or contact Marie or myself in the AIRAH office and we can send you through the details. But good job, Jesse, and I'll hand over to Marie to close up.
Thanks,
Thanks,
Brendan. And thanks, Jesse, for a great presentation and getting through all those questions. Thank you, everybody, for attending today's webinar. Just to let everyone know, the webinar has been recorded and it will be made available for AIRAH members up on the AIRAH website over the coming days, and we will let everybody know when that does become available as well. So thank you, everybody, and we look forward to seeing you again at our next webinar shortly. Thanks, Jesse. See everybody.
Thank you.